Good morning. Today we are going to discuss curvilinear coordinates and Dirac-delta function. Um, so far we have discussed the Cartesian coordinate system, which is made up by three mutually perpendicular axes x, y, z. And for the curvilinear coordinates, we're going to be using Einstein's convention. So instead of writing these as x, y, z, I would just denote them as simply xi, where I goes from 1 to 3. So x1 would be x, x2 would be y, x3 would be z, so on and so forth, right? And whenever we have two different things, for example, if I want to multiply two different vectors, then I would, in general, if I want to multiply two different vectors, I would in general write xi dot xj, because these two I and j need not be equal. But in this Cartesian coordinate system, we have a very special property because x, y, and z are mutually perpendicular to each other. Their dot products, if it is not with itself, the dot product is 0. So then we can say that if I take the dot product between two unit vectors xi and xj, then that is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. This comes from mutually perpendicular axis. So in general, then, I can write this as a function called the Kronecker-delta function. This is not the Dirac-delta function. We write it as delta ij. This delta ij is 1 if I is equal to j and 0 if I is not equal to j. So therefore, in general, we would write xi dot xj as delta ij, right? And similarly, we could also write the cross product. So then here, when we look at this Cartesian system, what we see is essentially any point x, y, z is defined as the intersection of three planes where x is equal to constant. So this is the y, z plane where x is constant, right? The y, z plane at x is equal to constant, for example. Or if I take y is equal to constant, then I have the x, z plane. And if I take z is equal to constant, I have the xy plane. So these three planes are intersecting to give me a specific point xyz. And these are special planes because they're flat, and they don't really need to be that. They can be any curved surfaces, in fact. So instead of writing any vector r as a function of xyz, I can choose any three surfaces. I can, in general, instead of choosing these xyz, these yz, xz, and xy planes, which are defined by these, I can choose any three surfaces. And in general, we say these surfaces are QIs. These are the generalized coordinates. So in general, I can take any three surfaces like Q1, Q2, Q3 that you see here, and express a vector r as a function of r of these Qi. So Ri of Qi. So this index is repeated. Whenever this index is repeated, recall that from Einstein's convention, this is summed over. So then if I want to write in general, what is the line element in these generalized coordinate systems? So the question we're asking is, if Qi goes to Qi plus dQi, what is the change in R? How does R change, right? So we are asking that question. So I can in general write dr as dou R by dou Qi dQi. Once again, this index is repeated, so that means it's summed over. So if I have three coordinates, this essentially means dou R by dou Q1 dQ1 plus dou R by dou Q2 dQ2 plus dou R by dou Q3 dQ3. So whenever you see an index repeated, it is summed over, right? And if we want the magnitude of this line element, I can write that as dr dot dr. Let's call it some dl square. Then I can write that as dou r. So in general, when we have two different vectors, we would use different indices I and j. So I would then have dou r by dou qi dqi dou r by dou qj dqj. So that we can write as dou r by dou qi, excuse me, yeah, dou r by dou qj dqi dqj. So here both I and j are repeated, so both I and j are summed over. But in general, we can represent this as a matrix. So I can write this as gij. So in general, I can write the dl squared, the magnitude dr I dot drj as gij dqi dqj. Again, these ij are repeated, so they are summed over, right? So now when we look at this dr back again, we saw that this is dou r by dou qi dqi. We're establishing these differentials because our ultimate aim is to look at how gradient, how divergence, and how curl would appear in these different coordinate systems. And the point of studying these different coordinate systems is sometimes the symmetry of the problem requires us to choose a different coordinate system. It is not that we cannot solve the problem in Cartesian coordinate system. It is rather that choosing, say, a spherical coordinate system makes the problem much easier. So we can write the line element dou r, dr as this. And again, remember that this I is summed over. But notice that this is actually a vector because it's dou r by dou qi, where r is a vector. So then I can write this vector dou r by dou qi in general as the magnitude of dou r by dou qi. And this is a tangent to the surface, right? We're taking tangent with respect to qi, so the direction would be along the unit vector qi. Right? So, for example, think about this in terms of Cartesian coordinates. If I were to write r as simply as a function of x, y, z, then by this we would have dr to be dr by dou xi dxi, which implies this dou r by dou xi for x-axis would be dou r by dou x magnitude dx along x plus same thing. We'll have dou r by dou z dz along z, and also the y component here, right? So you see that for dxi you get the x, for dz you get z. So similarly here we are taking the tangent, so we get the qi unit vector. And this magnitude dou r by dou qi, we're going to give it a name. We're going to call it hi. We call this as a scale factor. So this sort of tells us how different systems are related. So if we know the scale factors, then we know how to write this line element hi dqi, so we can perform all our integrations, divergence, and everything. For example, if I have a simple integral where I'm integrating a vector v, which is a function of qi dot dr, which I'm going to write it as function of j, because we're taking the dot product. In general, we write different indices to take the dot product. So when I say vi qi, once again, that means v1 q1 along q1 plus v2 q2 along q2 plus v3 q3 along q3. That's what we mean by vi qi. So then I can write this vi qi as simply vi qi, right? Sorry, I wrote it wrong here. Excuse me. So this should not be this q1. It's just v1, v2, and v3 along q3. I repeated that. That's my fault. So then I have vi qi. Vi is a component along qi. dot for dr, I have hi dqi is the magnitude, and the direction is q, this is j, so qj, because we chose a different index here. So then if I multiply these two, I would have vi is just a number, j, or a function, scalar function, dqj qi dot qj. We have seen this dot product on the very first slide. That's what we defined the Kronecker delta as. So this Kronecker delta is delta ij. So here, what we are saying is, if we are saying that this is equal to delta ij, we're choosing three surfaces that obey that orthogonality, that are mutually perpendicular. That's when the dot product is 0 if you have two different axes. So if we have such coordinate system, then this is non-zero only if I is equal to j. So then I can write this as I and j are equal, so I can just simply write it as vi hi dqi. And again, I is repeated here, so that's summed over. So this means the integral would look like v1 h1 along dq1 plus v2 h2 dq2 plus v3 h3 dq3. So as you can see, knowing these scale factors, h1, h2, h3, or hi in general, is what can help us write these differentials or gradients and divergences in different coordinate systems. So let's look at a simple case here. So let's look at so let's take a look at a simple polar coordinate system. So so let's draw x and y. So this is we're just going to look at it in 2 dimensions for now, and then we will extend it to 3 dimensions. So if I just have x and y, and if I have, let's say, any point r in this coordinate system, which is given by xy, and an angle theta, I can have two coordinate systems that way, whether it is xy or r theta. Both can define points uniquely. It is just that, here the lines are different. So then I can relate these two, xy to r theta. So in fact, I can write x as a function of r theta, which is r cosine theta, and y as a function of y r theta, which is r sine theta. So now if I want dx, if I would like to look at dx, then simply dx is dou x by dou r dr plus dou x by dou theta d theta. So this would be cosine theta dr plus, we're differentiating with respect to this, and minus r sine theta d theta. Similarly, I can write dy. Dy would be dou y by dou r dr plus dou y by dou theta d theta. So this would be sine theta dr, and this would be plus r cosine theta d theta. Now, in the xy coordinate system, if I were to ask myself that if I change x to x plus dx and y to y plus dx, dy, then what would be the net change in r, which goes to r plus dr? Then the net change in dr, which is a vector, would be dx along x-axis, and dy, let's call this x, along y-axis. But we know what this dx and dy are with respect to r and theta. So let's plug them in. So I'm going to plug in this for dx and this for dy. So then I would have cosine theta dr minus r sine theta d theta along x, and I'll have plus sine theta dr plus r cosine theta d theta along y. So now let's do a little bit of rearrangement here. So what I'm going to do is I'm going to club all the dr elements together. So I would have c theta dr along x, and I would write this next to it. So I would write sine theta. Let me just simplify it even more. So let's just say c theta dr, sorry about that, c theta along x plus sine theta along y, both have this dr term, right? And similarly, plus if I do r d theta, then I would have cosine theta minus sine theta. And cosine theta is along y-axis, and sine theta is along x-axis, right? So you can see that this is a vector and this is a vector, but we can also write dr. If I were to write r itself in r times theta, if I were to write r itself as a function of r and theta, right, then the dr would be dou r, sorry, so that would be dou r divided by dou r dr along r plus dou r divided by dou theta d theta along theta, right? Here notice that this r in r theta is the coordinate. Excuse me. So here then I can see these would be magnitudes, and this is what we would call HR, and this would be H theta, like we discussed about the scale factors. Now from here I can see that if I look at dr, then it looks like the magnitude of c theta along x and y should give me the magnitude for HR, right? And the direction would be obviously along r because it has both x and y. So then similarly I can write r times cosine theta y minus sine theta x, the magnitude of this to be h theta, which is this, right? So we're trying to identify the scale factors here, what the scale factors would look like. So then I can write what HR and H theta are. It's you see that it's sine theta and cosine theta. So the magnitude of HR is simply 1 because it would give you a square root of c theta square plus s theta square. But in case of H theta, you have a r dependence. In case of H theta, you have r, and this cosine theta sine theta would still give you 1. So just like this, so you would get H theta to be r. So in terms of polar coordinates, we have HR to be 1 and H theta to be r. These are not the flat coordinates that we have in XYZ. So that's why the scale factor need not be constant. It could depend upon the other coordinate. So that's important to note here. That's why these are curvilinear coordinates, because these scale factors are not necessarily constant. So once we have identified the scale factors, everything else becomes easy, because now I can write, because I know how to write dr. Dr is essentially hi dqi along qi. So now we have figured out that the scale factors are hr is equal to 1 and h theta is equal to r. Then I can write dr as, h1 is 1 times dr along r plus hi for theta is r, and that coordinate is d theta along theta. So the line element there would be r dr plus r d theta theta. Suppose now we extend this into 3 dimensions. we would have the spherical polar coordinates, and that's what is in the textbook. So now let's extend this to spherical polar coordinates. So in spherical polar coordinates, which is discussed in great detail in the textbook, um, we essentially have, instead of x, y, z, we have r, theta, phi in this. So if I have, let me erase this here and redraw it this way. So x, y, and z. So instead of this, we have now r, theta, phi. So instead of these flat surfaces like xy plane or yz plane or xz plane, now we have three different surfaces that are related to, instead of x being constant, but r being constant, or theta being constant, and phi being constant. So if I pick any point in general, x, y, z, I can have the direction, this direction as r, right? And the angle with respect to the z-axis is theta. And down here, if you project it, if you project this, then this angle is phi. So that's what forms the spherical coordinate system. So now if we look at what these surfaces are, for example, if you just look at, r is equal to constant, that means you're picking a point here and you want it to be constant in 3 dimensions. So you can imagine a sphere of that radius r, and the surface of the sphere should give you the constant surface r is equal to constant. Now similarly, if you look at theta is equal to constant, you can see that this line, you can sort of rotate it around. So you can sort of rotate it around into a cone, and that cone is the second surface, which is here theta is equal to constant. And if you pick a single phi, phi is along x and y axis. See that, phi is along the x and y axis. So if I take a constant phi, then for the constant phi, the surface would be a half plane along the z axis. So let me maybe use another color here so that you can more clearly see. So this half plane along the z-axis would be the surface for phi is equal to constant, and theta is equal to constant. Let me show that in blue, would be a cone. So instead of the flat x, y, y, z surfaces, now we are going to look at these three surfaces. And like we have seen, in general, we can approach any system by knowing the scale factors, right? So to know the scale factors, you can first, write x as a function of r, theta, phi here. In the previous example, we just wrote it as a function of r and theta, but now we're going to write it as r, theta, phi because there are three coordinates. So we would have r sine theta cosine phi, because this r, you project it along the z-axis first. If you project it along the z-axis first, you get r cosine theta along z, and then r sine theta along x and y. So you would get r theta phi for y would be r sine theta sine phi. So like in the previous example, you can now write out what dx, dy, dz are. And then you could also in general get the scale factors by combining, like in the previous example, you can get the scale factors there, and by using those scale factors, you can write how, for example, a line element dr would look like, right? So hr is simply dou r by dou x by dou r along I plus dou y by dou r along j, and dou z by dou r along k. the magnitude of it. Because we have seen in case of the two dimensions that when we did x is equal to r theta, right? We could see that if you combined, the dou r terms, that would give you this hr. So you can calculate what that is. So dou x by dou r is essentially sine theta cosine phi. Let me rewrite this as xyz just to be consistent, because I don't want to use I for an index and have you confuse that with the unit vector. So I want to be a little more careful about it. So dou x by dou r is sine theta cosine phi along x, plus dou y by dou r is sine theta sine phi along y, and this is simply cosine theta along z. And because this is HR, the corresponding direction for this HR vector would be R, right? So in other words, we can write the unit vector R as this, right? Sine theta cosine phi x plus sine theta sine phi y plus cosine theta z. And as you can see, the magnitudes of these would turn out to be, for example, if I take HR, the magnitude of this, that would be equal to sine theta squared cosine phi squared plus sine theta squared sine phi squared plus cosine theta squared, right? So I can pull out sine theta squared as a common factor here. Then I would have cosine phi and sine phi add to give me 1. And so I would essentially, from these two terms, I have a sine theta squared left out, and that would add to cosine theta squared and give me 1. So the magnitude or the scale factor for R is simply 1. Similarly, you can write h theta and h phi, and that's how you can get what r theta phi look like in terms of x, y, and z. So I hope this example makes it clearer as to how we obtain r theta phi in terms of x, y, and z, and how we get these scale factors, just like how we got in the polar coordinate system. You can do it. You can repeat that once more for the phi direction. So you would get r theta phi now instead of just r and theta. So now that we know how the line element should look like in general, like we discussed, the line element should look like simply dou r by dou qi dqi, or like we wrote hi dqi qi. Let's look at how the total gradient would look like, for example. So let's look at the gradient here. So before we look at the gradient, excuse me, note that dr is dou r by dou qi dqi along qi, and this is what we call as the scale factor, right? I keep stressing on the scale factor because that's all you need to know to go from xyz coordinate system to any other coordinate system. So essentially, whenever you want to look at different coordinates, you express xi, that is xy z directions in terms of the QIs, right? The Q functions, just like how we did for the polar or the spherical polar coordinates as x of r theta or y of r theta. And from there, by knowing dou x by dou r, dou y by dou r, dou z by dou r, dou z by dou r, for example, you could figure out what would be the scale factor for HR. So scale factor for HR was simply the magnitude of this, right? So figuring out the scale factors is easy that way by knowing the relationship between x, y, z and r theta phi or any other generalized coordinate system. Now let's look at the gradient. So the gradient, as you may recall, we originally took a scalar function, for example, temperature at each point, which was a scalar function. And then we build the gradient so that we can get the total change and also the direction of maximum increase. That's how we define gradient in a fundamental way. So now if I indeed have some function in general f, which I can write as a function of these QIs, it's a scalar function, then I can write this df, the total change, as dou f by dou qi dqi. So I'm going to do this, change this expression by dividing and multiplying it with hi. I'm going to write it as dou f by dou qi hi dqi. Now this is a scalar function, so here there is no direction. So now what I'm going to do is I'm going to take this hi dqi, and I know that dr, the vector, is hi dqi qi. So if I take dr and dot it with qi, for example, if I pick a particular q along, let's say qj, and dot it with dr, then that is essentially qj dot hi dqi qi. Hi dqi is not a vector, so hi dqi qj dot qi, and as you know, this is delta ij, so you get aj dqj. So by dotting dr with, say, an index j, I get that particular h j dqj. So then I can write this hi dqi as qi, because I want index I here, dot dr. And then if you look at this entire thing here, this is nothing but the gradient. You're taking a scalar function and you're looking at the change, and then you're giving it the direction along which, because you're taking the tangent for qi, so you're putting in that direction qi. So this is gradient. So in general, the gradient operator, gradient of f in general coordinates, is simply 1 over hi by dou f by dou qi, right? Qi. So if you look at just xyz, right, how would you express x as a function of itself, right? So x is x, y is y, z is z, right? So then naturally you can see that all the scale factors would be 1. So then I would have dou f by dou x along x plus dou f by dou y along y plus dou f by dou z along z. So then I would have essentially dou by dou x x, dou by dou y y plus dou by dou z z of f. This is what we saw initially as the gradient. So this is the general definition of the gradient, and you can get the scale factors by expressing x in terms of x of qi, and from there you can get the scale factors. And once you have the scale factors, you know how to look at the gradient. For example, if I take the spherical polar coordinate system, let's do this. Let's do this as an example, right? So as an example, we are going to derive scale factors for spherical polar coordinate system, and write the gradient in spherical polar coordinates. So we know that HR is simply a magnitude of dou x by dou r I plus dou y by dou r j plus dou z by dou r k. Similarly, h theta would be dou x by dou theta plus dou y by dou theta j plus dou z by dou theta k, right? And similarly, h5 would be the same thing. And we know what x and y look like as a function of theta and phi. So we know that it is r sine theta cosine phi, and y is equal to r sine theta sine phi, and z is equal to r cosine theta. Here, you have to be careful while using polar coordinates because of the convention of theta and phi. So when I write these coordinates, what I mean by theta is the angle from the z-axis, and what I mean by phi is the angle here in the projection. Some people use it the other way around. So it's a minor change, but you can often get confused between theta and phi. So bear in mind what theta and phi are. So we have these relationships. So from this, we actually have seen that this HR comes out to be 1. Let's see how h theta would be. H theta is essentially dou x by dou theta. So I have r cosine theta cosine phi along x. I promise to write this as x, y, z. I keep forgetting that. I'm sorry. X plus dou y by dou theta for y is again r cosine theta sine phi along y, and then dou by dou theta would be minus r sine theta along z. So now if you take the magnitude of this for h theta, to look at h theta, then I would have square root of r square is common all throughout, and I would get c theta square, c phi square plus c theta square, s phi square plus s theta square. And then again, you can see that the c phi and s phi add up to 1, and you get the result of adding the first two terms is simply c theta squared, which combines with sine theta squared to give you 1. So h theta is simply r, just like the polar coordinate system, h r and h theta there. Now, similarly, you can look at h theta, but you can see that for h theta, h phi, you see that the z-axis doesn't have any phi term. So essentially, you would get a very similar answer like this, except there won't be any phi term left along the z. So because dou z by dou phi here is 0. So then we have only dou x by dou phi along x, and then a dou y by dou phi along y, and this term is 0. So dou x by dou phi is simply r minus r sine theta sine phi along x plus r sine theta cosine phi along y. And then the magnitude of that for h phi would be square root of r square s theta square s phi square plus r square s phi square, s theta square, this should be theta, c phi square. Then I would have this to give me r sine theta. So like I said, because these are curvilinear surfaces, these are not flat surfaces like we have seen, like x, y, y, z, and zx planes. Here, the three surfaces we have are sphere, a cone, and a half plane. Right? Those represent the surfaces for r theta phi. And we have come up with the scale factors here by just establishing the relationship between x, y, z, and r theta phi. So then I can write hr is simply 1, and h theta is r, and h phi is r sine theta. Then I know how to write the gradient. The gradient is 1 over hi dou by dou qi along qi. So then the gradient operator in spherical polar coordinate systems, right, for r theta phi, we can write that then as 1 over hr is just simply 1 dou over dou r along r plus 1 over h theta is r, and so I have dou by dou theta along theta plus 1 over h phi is r sine theta. Then I have dou by dou phi along phi, right? So then I can write the gradient as dou by dou r plus 1 over r dou by dou theta plus 1 over r sine theta dou by dou phi. And because these are curves, the scale factors they're dependent. So r is there. and r sine theta. So similarly, you can write, you can also come up with what the divergence would be by going back to the fundamental definition of divergence. Recall that the fundamental definition of divergence was, if we had a vector field VA, we took the surface integral, right? Recall that where we divided, we had limit delta V goes to 0 over some small surface. We did V dot dA and divided it with delta volume. So that's how we define divergence. So now we can look at, how to write the integrals in this system. So if I want to look at how to write integral, for example, if I want to write some V dot dA, then for example, if I am taking, for example, two coordinates for I and j, because like in the xy system, if I have x, y, z, if I look at xy plane, the area element here, I go from x to y, so the area element is pointing up, for example, if I go right-handed, right? So the area element itself is dx dy, and it is pointing along j. So if I want to find out what this is, then essentially I have two different directions, right? So for each direction I have a dr, which is given by hi dqi, and the other one is given by hi dqj. Here, excuse me. Here, notice that you are not doing a dot product. To navigate and press space to toggle in. Excuse me. So here, here we are not doing a dot product. So this dx by dy is not a dot product. We are doing rather a cross product to get the area direction. So the cross product of x, y, the area element along x, y is z, but this is dx and that is dy. So these are the magnitudes of changes along x and y. So here you're not doing a dot product. So you're just looking at the magnitude. So simply hi, hj, dqi, dqj. And this would be along the direction qk, just like how x and y are along the z-axis. So if I want to write the surface integral for v dot dA, then I can write the surface integral as v is simply vi of qi, or I can write it as vi along the direction qi, dotted with our area element is this. Our area element is with the vector, right? With the vector, the area element has this qk. So I would have hi, hj, dou qi, or dou qj along qk, right? So then I would have this as surface integral of here already we use I, so let's instead change it to m so that there is no confusion with this I. So Vm hi hj dqi dqj, and I have qm dot qk, right? So m is repeated, so you would get three terms here because as m is repeated. So if I make let's say m is equal to 1, right? Then I'm only going to get the term with q1. So I would have this as integral of v1. Let's write the indices for these things in a while. So if I pick m is equal to 1, this product is given by delta mk here. So this would be non-zero only if m is equal to k is equal to 1. If I pick m to be 1, so then I necessarily have this along m is equal to 1. So if m is equal to 1, then I know what ij are. These should be 2, 3, because see here that if I have ij, I have k here. Like if I have x, y, I have z. So these should be 2 and 3 for v1. Now if I pick m is equal to 2, I add another term in the summation because I'm repeating m. So if I do that, I would get V2, right? And only the second component gets filtered out. So then I would have H1, H2, H1, H3, DQ1, DQ3. And then similarly for the third component, I would have V3, H1, H2, DQ1, DQ2, right? So that's how I would get this entire term, right? So if I want to do the do the surface integral, I evaluate these integrals. Now we have taken out the vectors out of them, so we just simply have this. So let's look at how this would be in spherical polar coordinates if you want to do a surface integral over any vector function. So we know this, right? So from here we can see how that looks like. So if I have a vector integral and I have um, um, along the area vector that is equal to V1, here I would have H theta, H phi, D theta, D phi, right? For basically, if I'm looking at R direction, I would have theta phi. So this would be VR, right? Then plus for V theta, I would have HR, H phi, D theta, sorry, DR, D phi. Similarly, for the phi, I would have V phi, HR, H theta, DR, D theta, right? So if I take a special function, if I take a special vector which is only a function of r and not of theta and phi. So let's look at that such a function here. Let's say 1 over r square r. We are going to encounter such functions a lot. 1 over r square, as the electric field, magnetic field, all these things fall off as 1 over r square. So let's pick a function v is equal to 1 over r square r. So it only has the r component. So it's v theta is 0 and v phi is equal to 0 and vr is simply 1 over r square. Then as you can see here in terms of integrals for this particular special function, which is only a function of r, right? Then I have, if v is only the function of r, then I have that to be vr h theta h phi d theta d phi. And we have determined what these h theta and h phi are. H theta is r and h phi is r sine theta. So then this surface integral would be VR r squared sine theta d theta d phi, right? So if I want to integrate something like this, 1 over r squared, let's see what would happen. So I know this is just the VR component is 1 over r squared. So if I plug that in, I would have 1 over r squared times r squared sine theta d phi. So if I integrate them out, then I'm going to get an integral for theta. Theta is the angle with respect to z axis, right? So theta is with respect to the z axis. So it goes from 0 when it is aligned with z axis to semicircle pi, right? When it is at the other end. So it is going to go from 0 to pi for d theta. And for phi, it goes full circle in xy axis. So for phi, we are going to go from 0 to 2 pi. So the integration for phi is easy. 0 to 2 pi d phi simply gives you 2 pi. And if you do 0 to pi sine theta d theta, right? Then that's going to give you another factor of 2, because it is between 0 and pi and 2 pi. Sorry, and oh, sorry, it should be pi. So it should be pi. That's going to give you another factor of 1. So then, because integrating sine theta would give you cosine theta, and cosine theta is 1 when it is 0 or pi. So you would get another factor of 2 from here. So this would overall give you 4 pi. So what we basically looked at was we looked at how to integrate a function like 1 over r squared r in spherical polar coordinates. But in general, if you want v theta v phi, any function, just like how we did this VR component, you would do VR and v phi. And we picked this specific example here because it's very relevant for us. And what we have seen is that if I perform the surface integral of v dot d sigma, then over the area element for this particular function, 1 over r squared, then I get 4 pi. And this makes sense physically because imagine something here like a charge or something like a gravitational mass, then you know that the electric field, although we have not yet discussed electric field so far, we're going to talk about it, but you know Coulomb's law in a way. What that you know that the electric field is somehow going to go as 1 over r squared, so it's sort of radiating out, uh, depending upon the charge you can say, but you can see that it's a source. It's like having a faucet when we discussed divergence. So it has a source, so it is constantly going outwards. So you would expect the divergence, as it is pointing out, you would expect the divergence to be positive, right? Because if I take it is the length of the arrow is decreasing as you're going out because it is 1 over r squared, right? So if I take at any point the arrow that is coming in is longer than the arrow that is going out, so that should mean positive divergence. And we see a value of 4 pi, so it makes perfect sense. But if we follow like how we have derived the gradient to be 1 over hi, dou I dou qi along qi, if we follow such a derivation for the divergence, that would give you, for example, the divergence in spherical polar coordinate systems. If I have del dot v based on these scale factors, it would look like 1 over r squared dou by dou r squared along r plus 1 over r sine theta. These are the scale factors that would come into picture for divergence. Just like how we derive the gradient, you could derive this as well using the scale factors, dou by dou theta, sine theta along theta, plus 1 over r sine theta dou by dou phi along phi. So you would get basically this sort of a thing there for a vector field. Notice that you cannot take this directly and like how in case of Cartesian coordinates for doing del dot v, we directly took the same form as gradient, but that's not the fundamental definition of divergence. This is the fundamental definition of divergence. So bear that in mind. So this is how the gradient operator it looks like in spherical polar coordinates. It's also in the book, and the way you derive it is using these HIQIs. We're not going to go into the mathematics of it, but I will nonetheless upload some lecture notes on that so that if you're interested, you can work it out. And also there will be some homework questions to derive the divergence in cylindrical polar coordinates or spherical coordinates. So you will come up with this the way we derived gradient. So if I use this definition, then I have only VR component of 1 over r squared in this function. So only this is relevant. So the divergence of v, which is only a function of r, would be 1 over r squared dou by dou r squared, and my function VR is 1 over r squared. And we're taking only this component because our function is only along r. So now r squared and r squared cancel out, and this comes out to be 0. So if we go by the surface integral, we see that the divergence for this function 1 over r squared r should be a positive number, 4 pi. And our physical explanation with a faucet here, for example, if I have a source of water here and the water is going out, and if it is going off as 1 over r squared, we saw that physically when we put a sphere here, we see that it should have positive divergence. But if you do the just pure math, you would see that it should come out to be 0. And this is another reason why putting physics first is important, because you can see, these kind of things can happen where physically the divergence is positive, but equation looks like it is zero. So this comes out to be zero because it is not accounting for the point at r is equal to zero. It's not accounting for this source, this faucet that is at the center at r is equal to zero. So to include that center into our description, we introduce something called the Dirac-delta function. Strictly speaking, a Dirac-delta function is not really a function because it has infinite value. So the way we define a Dirac-delta function is if I have in general three coordinates, right, r, then this is equal to zero everywhere other than r equal to zero and infinity at r equal to zero. So in case of x, y, z coordinates, you can write this delta function as essentially a delta function along x, a delta function along y, and then a delta function along z. So there is a huge infinite spike at the center. So if I have x, y, and z, it goes to infinity right there, and it is zero everywhere else. And you can also shift this around. It doesn't have to be at r is equal to zero. If you want to shift it around, if you want to shift this to say if you want to shift this to another place, then I can write, for example, to another constant a. So we want it to be zero when r is equal to a. Then I can write this as r minus a, right? So then that would be simply, delta of x minus a, and so on and so forth, delta of z minus a. So I can, so if I look at delta of x minus a, instead of being, so this would be zero everywhere x is not equal to a, and infinity when x is equal to a. So you're just simply shifting the origin. So to include a source at the center, we use this delta cube r. And so we let's look at one property, integrative property of this Dirac-delta function. So if I have a function f of x, and I'm going to integrate it with dx, but let's say I add a factor here, delta of x. This is the Dirac-delta. So at this, in this, what happens is this delta of x is equal to zero everywhere except x is not equal to zero. I'm sorry, I put it wrong. So this delta x is equal to zero everywhere, everywhere else except x is equal to zero. So by integration, we mean essentially, if I have some function f of x, I'm dividing this into smaller and smaller pieces, right? So this is, let's say, f of x, and this is x. So within each point, I'm taking some xi here, and then looking at this rectangle, right, and calculating the area and summing them up. That's what I'm doing while integrating. Now, if I do a product of f of x delta x, notice that delta x is zero everywhere else. So even if f of x has a positive value here, because delta x is zero, this entire product would be zero everywhere except at x is equal to zero. So when we integrate f of x delta x dx, we get this is equal to f of zero. So the thing that you have to note here is when we say delta x goes to infinity, right? The delta x is infinity. This is a mental construct. This is not real. It's like the calculus limit here. In the limit, when we are looking at integration, we're seeing in the limit delta x goes to zero, or basically you're dividing the line infinitely, right? So you are not doing it in actuality, but you are doing it as a mental construct. So this integral of f of x delta x dx would be f of 0. So in general, if I have f of r and delta r, then which is a function of a vector, and I can write it as r minus a vector dr or dv, a volume integral, let's say, which would be equal to simply f at a. And this is in 3D, right? So, so going back to our divergence of 1 over r squared, what we needed to do was include the source at the center, the faucet at the center. Because we have a faucet or a source at the center, the divergence is positive. So we would rewrite del dot 1 over r squared along r. This was the function we had chosen as 4 pi with delta cube r. So it is 4 pi only at the center, and everywhere else it is 0. So that it is in line with our volume integral v dot d sigma, which is the fundamental definition of divergence. So divergence of 1 over r squared would give you 4 pi times the delta function. So if I take gradient of a function like 1 over r, this is a scalar function 1 over r. So if I take the gradient of it, I would get minus r over r squared, right? And then if I take another divergence of this, of the gradient, then that is divergence of negative r over r square. So that would give me negative del dot r over r square, which is same as this. So this would be negative 4 pi delta cube r. And here we're doing the divergence of gradient. So this is scalar Laplacian. So it is acting on a scalar function like 1 over r, and then it gives you this result. So this is what we would call as the scalar Laplacian. So that's the thing we need to know about delta function as we go into the later chapters, where we are going to use this delta function often to represent the source or the faucet that is leading to a positive divergence. Right. So we will stop here, and then in the next lecture we'll start from chapter 2, where we start discussing electrostatics. So we have now the mathematical basis for it. So we're going to continue with that and go into electric fields.